نبدأ بالأستاذ توبي هاف، وهو باحث في سوسيولوجيا العلم وحاليا أستاذ مشارك في جامعة هارفارد، ويهتم بالخلفية الثقافية للعلم. سيلقي عرضا بعنوان الخلفية الثقافية العربية الإسلامية للثورة العلمية، ولا شك أن العنوان في شكل سؤال. Toby E.Huff, how do you say you have the floor? Yeah. The floor, please, 20 minutes.
Thank you very much. I want to thank the organizers of the conference for being so open-minded and ecumenical by inviting people with a broad range of views such as mine. Alhamdulillah. I hope my paper won't be too radical or revolutionary. For the past 4 years, I've been studying the European scientific revolution of the 17th century. In its larger contours, it was richer, more comprehensive, and more experimental than what the standard accounts generally tell us. From 1600, the very first year of the 17th century, exceedingly important experimental inquiries were carried out and reported on. There was an amazing amount of experimental inquiry going on all over Europe long before the founding of the Royal Society of London in 1661. The invention of the telescope in 1608, and then Galileo's use of it the next year, opened a whole new vista of scientific inquiry. With this new discovery machine, as I shall call it, the science of astronomy was propelled from a slow, plodding inquiry into a new and dynamic exploratory science. In that connection, the fact has been overlooked that the telescope was taken all around the world in the decade and a half after Galileo's discoveries were announced in his Starry Messenger of 1610. Indeed, the Chinese in 1615 had a report written in Chinese telling of Galileo's discoveries, including a diagram of the strange handles of Saturn, which of course were the rings yet to be identified. Similarly, the telescope was in the hands of the Ottomans, the Persians, and others in the Middle East, and along with the Hindus and Muslims of Mughal India, in some cases as early as 1615. But there was no significant scientific response from those quarters of the world when they received the telescope. Nevertheless, for the last 40 to 50 years, historians of Arabic science have been giving us new detailed studies of the high levels of technical achievement attained by Muslim astronomers during and after the Moraga period of the 13th century. Many studies have drawn attention to advances in mathematics, especially in trigonometry and algebra. Likewise, the advances in optics achieved by Ibn al-Haytham have received considerable attention, along with the explanation of the rainbow put forth by Kamal al-Din al-Farisi and al-Shirazi. Thereafter, optics in the Middle East fell into quiescence, while it was an Italian craftsman in Florence who invented spectacles in 1286. A little more than a century later, thousands of pairs of spectacles were being manufactured in Italy and shipped all over the world, especially to Istanbul, but also to Mughal India. Despite all this, the great hope of finding major scientific contributions from the Middle East in the 13th and 14th centuries has been pinned on the prospects of finding a major influence on Copernicus, either through the work of al-Tusi or Ibn al-Shatir. There appears to be similarities between some planetary models in Ibn al-Shatir's models and those of Copernicus, yet it remains true that there are no heliocentric models in any of the works of the Middle Eastern astronomers whose works have been found and examined. Consequently, the connection with Copernicus remains tenuous at best. So let let us try to get beyond these technical considerations in order to highlight some of the unresolved problems that had to be surmounted in order to arrive at the new science of astronomy that would produce a unified system of celestial and terrestrial mechanics governed by the law of universal gravitation, which was spelled out by Isaac Newton. If we think about the great challenge of getting to Newton's grand synthesis in broad terms, it is obvious that there were half dozen or more fundamental principles that had to be worked out. A short list of these would include the following. First of all, the Ptolemaic system had to be replaced by a heliocentric system. Kepler's work and, of course, Newton's were predicated on this assumption of a sun-centered universe. Second, Kepler saw what was needed in Copernicus's new system. It was the idea of a celestial physics based on physical causes. He was the first to announce this agenda and recognized that Copernicus said nothing about it, nothing about what physical causes might be operative in the universe. Likewise, it would be difficult, very difficult, to find an Arab astronomer who believed that some set of naturalistic physical causes govern the universe. Studies of Ali al-Kushti's writings, for example, of the 15th century, show that he was much more inclined to believe in the will of God than the forces of nature, which Aristotelian natural philosophy was always predicated upon. Third, another problem. It is evident that the Newtonian synthesis needed the law of free fall and the law of inertia, both formulated or articulated by Galileo, though sometimes not so clearly. Fourth, in the actual working out, in the working through of his synthesis, Newton needed Kepler's amazing third law, the one stating that there is some kind of physical constant in the orbits of the planets, such that the square of the period divided by the cube of the distance from the center of the sun is the same for all planets. To the degree that this mathematical formula, based on mean periods of revolution, was mathematically correct, it was an advance on Copernicus's original idea that indeed there is a relationship between the distance of the planets from the sun and the time it takes for each of them to revolve around the sun. Kepler's formula is a magical and inexplicable conception that is at once near and far from Newton's idea of universal gravitation. Kepler had a very poor explanation for the constant. He believed in an amalgam of magnetism and the mystical powers of the sun to push the planets around their orbits. Nevertheless, it was a sort of ground zero on the way to Newton's synthesis. Most important of all, let us notice that at the heart of astronomy, as part of the new physics, is the science of mechanics or motion. In other words, planets are like projectiles, and figuring out how the planetary system works required a new science of motion. Only those natural philosophers who had studied and advanced this discipline could contribute to the new science of mechanics at the center of Newton's revolution that was to emerge in the 1680s. There are other essential elements missing in this sketch, but given the shortage of time, I return to our underlying question. How does the Arab Islamic background fit into the picture? The first thing to observe is that with regard to the sun-centered universe and the discovery of the relationship between planetary orbits and their distance from the sun, there is no hint of this in the Arab sources that I know of. Ever since Noel Sverdlow made his claim for a connection between Copernicus and Ibn al-Shatir, it has been assumed that sharing any set of orbital parameters, though all were derived from Ptolemy, must mean a real connection exists. But the problem is the fact that since the time of Ptolemy, astronomers had worked with the same mathematical tools and the same Ptolemaic parameters for planetary orbits. The historian of mathematics, Otto Neugebauer, stressed his point. He observed that comparing the tables of the parameters of the 5 planets, Saturn, Jupiter, Mars, Venus, and Mercury, in Copernicus and Ptolemy, I'm quoting, the Copernican tables will produce practically the same results as the Ptolemaic ones. Essentially, no new observations were added even in the time of the 13th century reconstruction of the Alphonsine tables in the 13th century. Although Copernicus did make some observations of his own, in addition to eclipses, this was done mainly to confirm the accepted values taken from the sources such as the Alphonsine tables. Otherwise, the identity of the Alphonsine and Ptolemaic parameters has been shown by computer calculations carried out by Owen Gingerich. Consequently, the parameters for all the planets, not just Mercury and the Moon, were based on the Ptolemaic values. From this, it should not be surprising that the models of planetary orbits in Copernicus and Ibn Shatter converged and were in some places identical. If we assume that Copernicus was tracking or tackling the same problems in astronomy as the Arab and Persian astronomers in 13th century Moraga, was pursuing the same astronomical objectives, using the same methods and the same data from the Ptolemaic Alphonsine tables, it is by no means remarkable. The historian of astronomy, Mario de Bono, has suggested that Copernicus, quote, obtains results very similar to those of his predecessors. Furthermore, the reciprocation device, often referred to as the Toosey couple, could equally well have been derived from an independent reflection on these same problems. And there are other pre-Arab sources of the mechanism pointed out by other historians of science. Most important of all, it is the orientations of the two systems, one heliocentric and one geocentric, that are radically different. In the meantime, no one has shown that Copernicus actually had access to Arabic documents or others that contain the Toosey mechanism or Ibn al-Shadra's models. Likewise, no one has shown that having access, hypothetically, to this material had anything to do with Copernicus's thinking that led him to his heliocentric models. But let us turn now to perhaps the most plausible case for an Arab Muslim facilitating influence on the path to modern astronomy, the role of the Middle Eastern and Hindu mathematics. The Hindu-Arabic numeral system was invented in India sometime before during the 7th century and transmitted to Syria in 662 by Severus Sebokht. Soon thereafter, the system of 10 numerals, including a 0, was adopted by the Persian scholar Al-Khwarizmi around 825. It came to Europe in the late 10th century. Slowly, over centuries, hundreds of years, it was adopted for use by Europeans, although a mix of Roman and Arabic numerals continued to be used through the time of Copernicus. Indeed, Copernicus himself used such a mixture of these in the revolutions of the heavenly spheres. He used Roman numerals for angles and for dates, as well as for years and days. But he used Arabic numbers, which he called Hindu numerals, for lengths of measurement. However, the prime operators, plus and minus, were not added to the system until the 15th century by Europeans, and the equal sign was introduced by Robert Record around 1557. Consequently, Copernicus did not know the modern algebraic notation, so that as his translator, A.M. Duncan, put it, Copernicus's, I'm quoting, notation and expressions are entirely geometrical, following the Greek sources. Likewise, Newton had invented some elements of the calculus in the 1660s, but his full system did not emerge until after the publication of his Principia. had been published in 1687. Consequently, his master work is a work of almost pure geometry, not algebraic calculation. His Principia contains no equal signs. But it is generally recognized that Middle Eastern mathematicians did a great deal to consolidate and develop trigonometry. The consensus among historians of Arabic Islamic science is that the Arabs were indisputably the founders of a plane and spherical trigonometry, which, properly speaking, did not exist among the Greeks. What this meant was that calculations of the sizes and dimensions of planes and spheres, triangles, and related figures were greatly simplified. By the 10th century, the mathematical functions known as sine, cosine, and tangent, along with their tables of application, had been invented in the Middle East. With the great translation movement of the 11th and 12th centuries, these mathematical advances were brought to Europe, along with translations of Ptolemy's astronomy, known as the greatest book, the Almagest, by the Arabs. Even so, just when and from whom Europeans learned of the rich details of trigonometry remains somewhat obscure. The most important consolidator and transmitter of the new trigonometry was the German mathematician and printer Regiomontanus, also known as Johann Müller, who later taught mathematics at the University of Vienna, though he also traveled around Europe a great deal. But it was his teacher, George Feuerbach, who launched the detailed study and assimilation of Ptolemy's Almagest. Though Feuerbach died prematurely, he and Regiomontanus produced the most important European work in astronomy of the Renaissance, the epitome of the Almagest. Can't do it. What is significant in the present context is the fact that Regiomontanus wrote a work on triangles, and which was published in 1533, and which did get input into his Revolution Ibus. But even if we know that Copernicus used trigonometry, the exact path of it doesn't give us the key to his revolution. The path, or the exact path, of Copernicus's revolution, heliocentric revolution, is not fully understood. Even though it is not, it involved both the transformation of epicyclical models into eccentric models, apparently using a geometrical transformation device articulated by Regiomontanus, and which has been found earlier in the writings of al-Kushji. The transformation that Copernicus made involved at least two steps. By using the transformation device, Copernicus realized that you could get the same observational results by shifting the center of the stacked planetary orbits to a sun-centered model that he adopted, something not achieved by any of the other astronomers who knew about the parallelogram transformation device. Secondly, Copernicus then scaled his models according to the ratio of the epicycles to the larger spheres, the deferents, and when he did so, he discovered that the periods of the planets corresponded to their distances from the sun. This naturally was very pleasing to Copernicus and made him think that this must be the real arrangement of our planetary system. However, Copernicus got to that heliocentric point. It is clear that Middle Eastern astronomers failed to get there. Let us turn now then to other large lacuna in the science of motion that was needed for the grand synthesis. This brings us finally to the centrality of mechanics in the science of motion, without which the great leap to Newton's synthesis would not have been possible. Physics and the science of motion had been central to Aristotle's physics since before Aristotle's time. On the other hand, astronomy in Aristotle's conception of the sciences was located among the mathematical, not the natural sciences. It was for that reason that astronomy was seen as a mathematical model-building enterprise, not a natural science, legislating the shape of the world. What that meant is that in the great long run of scientific inquiry, leading to the modern scientific revolution, Those two disciplines had to be brought together, as they ultimately were in Newton's mathematical principles of natural philosophy. In the extended interval before that accomplishment, progress had to be made in the science of mechanics as well as astronomy. But in the Muslim world, very limited progress was made throughout the so-called Golden Era. It ended altogether in the early 12th century. The last significant contributor to the science of motion was Ibn al-Bajjah, the Andalusian Muslim philosopher of the early 12th century. There are indications that some of his thinking did aid medieval Europeans. But after him, historians of science have failed to find any successors of his caliber. Neither the Ottomans nor the Moguls wrote significant treatises on the science of motion in the years between Ibn al-Bajjah and Galileo and Kepler. And Ibn Bajjah's contribution to the science of motion that was actually rejected by Averroes was the notion that if you take away the force surrounding an object, the air, the speed of the propelled object would not be instantaneously infinite, but would reveal the natural motion of the object. But that realization is a long way from Galileo's law of inertia, as well as his law of free fall. So it is apparent that what was needed to get to Newton's grand outcome, a synthesis was needed of Kepler's 3-2 law, Galileo's law of inertia and free fall, and the proof that if an object falls toward the Earth, its trajectory would be an ellipse, and the force involved would vary inversely with the square of the distance between the centers. Sir Christian, Robert Hooke, and the young Edmund Halley all knew this result must be right, but only Newton could prove it. Moreover, Newton achieved his great synthesis not by using algebra, trigonometry, or calculus, but by using geometry. Neither the Moguls, Ottomans, nor Persians, or the Chinese for that matter, were on the path to a new unified science of celestial and terrestrial physics. Thank you.